Hello and welcome to the following lesson on work and the conservation of energy, which is part of the Forces and Motion module for OCR A-Level Physics. So in today's lesson we're going to be looking at work and the conservation of energy. So going to look and understand and calculate energy in different stores. So if we've been successful and we've learned in today's lesson, we should be able to describe what happens when work is done on an object, describe the energy changes in a closed system, and then calculate the work done or values associated with it in a system. So we're going to be looking at the following part of the OCR A-Level Physics specification. 3.3.1 Work and the conservation of energy. So energy is the ability for an object to do work. The principle of conservation of energy states that energy cannot be created, cannot be destroyed, it can be only transferred from one form to another. So this means that the total amount of energy in a closed system remains constant, although how much of each form there is may change. So whilst energy cannot be created or destroyed, only transformed from one store to store, or transferred from one type to another type, if it is caused by a resultant force acting on an object, we say work is done. So in this situation here, the gravitational potential energy store is had work done. The objects then had work done to it to turn it into the kinetic energy store. Now an isolated or closed system is occurring in this energy transformation as none of the energy is being lost to the surroundings. Now all transformations or transfers of energy are not isolated, and all of them will have energy going to the internal energy store of the surroundings due to resistive forces. Now we can use the transfer between energy forms to calculate the values of an object, and this is done by considering the properties of the energy type in each form. Now there are two types of energy forms. There are energy stores, when energy is stored in an object, and energy transfers, when energy is moved or causes movement. So we'll focus first on energy stores, when energy is stored in an object. The first type is elastic potential energy, the energy of a stretched elastic object. Then we've got gravitational potential energy, the energy of a massive object inside a gravitational field. We have chemical energy, the energy contained in the chemical bonds of a substance. Nuclear energy, the energy contained in the nucleus of an atom. Internal energy, the energy contained in the particles of a substance. We also have energy transfers, when energy is moved or causes movement. So kinetic energy, the energy of a moving object. Sound, light and electrical energy. They're ways in which energy can be transferred in a system. Now when energy is transferred from one store in a system to another store in a system, work is done. Work done is energy transferred in a system. So work done refers to the transfer of energy to store without the explicit need for a wave. So whenever work is done, the total amount of energy after the transfer is always equal to the total amount of energy before the transfer. The total amount of energy is unchanged because energy cannot be created or destroyed. The total energy before is equal to the total energy after. This is the principle of the conservation of energy. Now two factors affect the work done when moving an object. The first one is the size of the force. The bigger the force, the greater the amount of work you do. The second is the distance that you push the object, s. The further you push it, the greater the amount of work done. So the bigger the force and the further it moves, the greater the amount of work done. So we can calculate the work done in a system with the equation work done in joules is equal to the force in newtons times by the distance moved in the direction of the force in meters. Now we can define 1 joules in terms of this. 1 joule is therefore going to be 1 newton times by 1 meter. So 1 joule is 1 newton meter. It is also defined as the energy transferred to, or the work done on an object when a force of 1 newton acts on that object parallel to its motion through a distance of 1 meter. So we could also define it in terms of SI base units. So 1 joule is equal to 1 kilogram meter squared per second squared. Now work is the energy that has been changed from one store to another store. This does not have to be the total energy of the object. The value that this calculates is the change in the energy store, not the total energy store of the object. Now this equation does assume that the direction of force is the same as the direction of movement. And this equation also assumes that the size of the force is a fixed value, either it's a constant or average force. So if a constant force F acts on a graph and makes it move a distance s in the direction of the force, the work done on the object is W equals Fs. So this tells us that the area under the line of a force distance graph is the work done on the object. Now from Hooke's law, we are aware that the force required to stretch an object increases in direct proportion to the change in length it causes, which is the distance, for that elastic object. So in this case, the area under the line of a force distance graph is the work done on the object. And in this case, it is the work done, the energy is being transferred into the elastic potential energy store. So it'll be a half force times by distance, because that is the area under this line. Now, if a variable force F acts on an object, it makes it move a distance delta S in the direction of the force. So therefore, the work done is going to be delta W equals F delta S. So the area under the line of this force distance graph is the work done on the object. Now, as the area is variable, the area under the line should be split into different strips. So the area under the line here is still the work being done on the object. However, you've got to work out the sum of all of the values of each of the strips. Now, when work is done against friction, this will cause heat energy to be transferred to the internal energy of the surroundings. Friction can act as a resultant force which makes energy change stores in the process. So friction can cause some of the energy to be transferred to the thermal energy stores, which can cause the overall temperature of the object to increase, which is shown by people rubbing their hands together to keep warm. So let's consider the following example. A box is pushed across the floor with a constant force of 100 newtons. What is the work done by the force to move the box 5 meters? So we know work done is force times by displacement, so it's 100 times by 5, so it equals 500 joules. Now, if the box is now dragged by a rope which is raised at an angle of theta to the horizontal, this time the box moves in a different direction to the direction of the applied force. So you must find the component of the force that acts in the direction of the movement. You must resolve the force into the direction of the motion. So when calculating the work done by a force acting at an angle, it's useful to break the force down into components. For example, here, the tension in the rope can be broken down into horizontal and vertical components. The vertical component does no work because the box does not move vertically, it does move in that direction. Work is only done in the direction it moves in, the horizontal. Now we calculate work done by a force at an angle by saying work done is force in the direction of movement times by the displacement, which is most likely the horizontal. So W is equal to Fs cos theta. Now no work is done when F and S are at right angles to each other. This is because if theta equals 90, well then cos 90 equals 0, so no work is done. So let's look at the following example. Consider this. A toy car is pulled along by a piece of string which is at 30 degrees to the horizontal. Calculate the work done in pulling the toy if the tension in the string is 10 newtons and is pulled along 5 meters. So we say work done is force times by displacement times by cos theta. 10 times by 5 times by cos 30 is 43 joules. Next, you drop a stone weighing 5 newtons from the top of a 50-meter high cliff. What is the work done by the force of gravity? So the force on the stone is equal to the pull of gravity, which is the weight of the stone, which is 5 newtons vertically downwards. The distance moved by the stone is 50 meters vertically downwards. So since F and S are in the same direction, there's no problem. So work done is force times by displacement. It's 5 times by 50 is 250 joules. Now, the stone, with 5 newtons, is rolled down a 50-meter slope. What's the work done by the force of gravity? Now here, the distance moved by the slope down the slope is 50 meters, but the distance moved in the direction of the force is only 30 meters. It's only vertically downwards. So therefore, the work done by the force of gravity is 5 times by 30, which is 150 joules. Finally, a satellite orbits the Earth at a constant height and at a constant speed. The weight of the satellite at this height is 500 newtons. What is the work done by the force of gravity? Once again, the force on the satellite is the pull of gravity, the weight of the satellite, which is 500 newtons towards the centre of the Earth. However, the distance moved by the satellite towards the centre of the Earth, the direction of the force, is actually 0. So the satellite remains at a constant distance from the Earth. It doesn't move in the direction of F, so therefore the work done by the Earth's pull on the satellite is 0, because F is equal to 500, but work done is Fs cos theta, so it's 500 times by 0, which is 0 joules. So in today's lesson, we've looked at work done by a force, the unit of the joule. We've then looked at W equals Fs cos theta for the work done by a force. We looked at the principle of conservation of energy, energy in different forms, transfer and conservation, and the transfer of energy is equal to work done. So if we've been successful and we've learned in today's lesson, we can describe what happens when work is done on an object. We can describe the energy changes in a closed system, and we can calculate the work done or values associated with it in a system. Hello and welcome to this video on energy systems, which is part of the Forces and Motions module for OCR A-Level Physics. So in today's lesson we're going to look at how to understand and calculate energy in different stores. So if we've been successful and we've learned in today's lesson, we should be able to calculate the gravitational potential energy store in a system, calculate the kinetic energy store in a system, then calculate the values associated with the transfer of energy in a system. So in today's lesson we're going to be looking at the following part of the OCR A-Level Physics specification, 3.3.2, kinetic and potential energies. So energy is the ability for an object to do work. The principle of the conservation of energy states that energy cannot be created, it cannot be destroyed, it can only be transferred from one form to another. This means that the total amount of energy in a closed system remains constant, although how much of each form there is may change. Now, as we know, energy cannot be created or destroyed, only transferred from one store to another store or from one type to another type. But if this is caused by a resultant force, we say that work is being done. As in this example here, where the gravitational potential energy store of an object is changed into kinetic energy store of the object, so therefore work is done. Now, in an isolated or closed system, this means that the energy transformation is occurring when none of the energy is lost to the surroundings. However, all transformations or transfers are not isolated. All of them will actually dissipate some energy to the internal energy of the surroundings due to resistive forces. Now we can use the transfer between energy forms to calculate values of an object, and this is done by considering the properties of the energy type in each form. Now there are two types of energy forms: energy stores, where energy is stored in an object, and energy transfers, where energy is moved or causes movement. So if we think of our energy stores first, we have elastic potential energy, the energy caused by the stretching of an elastic object. Gravitational potential energy, the energy of a massive object inside a gravitational field. The chemical energy, the energy contained in the chemical bonds of a substance. Nuclear energy, the energy contained in the nucleus of an atom. And the internal energy, the energy contained in the particles of the substance. Whilst for energy transfers, we know about kinetic energy, the energy of a moving object, and sound, light and electrical energy, ways in which energy are transferred in a system. Now, when energy is transferred from one store to another store, we say work is done. So work done refers to the transfer of energy from one store to another store without the explicit need for a wave. And as we mentioned before, whenever work is done, the total amount of energy after the transfer is always equal to the total amount of energy before the transfer. So the total amount of energy is unchanged. The total energy before equals the total energy after. The principle of the conservation of energy. So let's now have a look at a few of these stores. Now, gravitational potential energy is due to the position of an object in a gravitational field. If an object of mass m is lifted at a constant speed by height of h, we can say that its acceleration is 0. Now we know that F equals ma, so we can also say the overall resultant force is 0, which means that the lifting force of our object is equal to the weight of our object. So we know the resultant force will be equal to the weight of the object, which is equal to mg, and the work done is the force times by the displacement. So we can substitute in the weight as the force into that work done equation. So m times by g times by displacement, which will change to height. So therefore work done is equal to mgh. So our gravitational potential energy store is equal to mass times by the gravitational field strength times by delta h. Now delta h is the change of height of an object in a gravitational field. Now this equation is only true when delta H is much lower than the radius of the Earth, otherwise the value for g, the gravitational field strength, varies and invalidates the equation. So this equation for gravitational potential energy is an approximation for when delta H is small. The true equation for gravitational potential energy is gravitational potential energy is equal to big G, big M, m over r. Now, gravitational potential energy is gained when an object moves higher and is lost when an object moves lower. Now, the potential energy is the energy an object has because of its position or shape. Now, often, potential energy is hidden or stored in an object. So, for example, an object's gravitational potential energy changes when it moves through a gravitational field. So we can identify some other forms of potential energy. So for example, an electrically charged object has electrical potential energy when it's placed in an electrical field. An object may have elastic potential energy when it's stretched, squashed or twisted. If it's released, it goes back to its original shape. Now, kinetic energy is the energy a moving object has. The faster an object is moving, the greater its kinetic energy. So let us consider a car that accelerates from being stationary, u equals 0, to travelling at velocity v when a force F is applied. So if we know v equals u plus at, this is one of the Suvat equations, we know that v in this idea will be equal to at, it will be acceleration times by time, and we know that t is equal to v over a. So now we also know that s equals a half u plus v times by t. So with that, we can sub in our equations now and say s equals a half vt, because we know u in this concept is 0. So therefore it equals a half times by v over a. So therefore it equals a half v squared over a. Now we know work done is force times by displacement. So we know that the force is mass times acceleration, F equals ma. And we know that the displacement is s. So we know that from the previously it's a half v squared over a. So it's m times by a times by a half v squared over a. So we can then simplify that to say our kinetic energy store is a half mv squared. Now this equation only works at classical velocities. Velocities much lower than the speed of light. When you approach the speed of light, the mass of an object increases, invalidating the equation written to the side. Now this equation also indicates that kinetic energy is directly proportional to the mass of the objects travelling at the same speed. It also indicates that kinetic energy is directly proportional to the square of velocities of given objects. Now in a crash, a lot of kinetic energy is transferred in a short space of time. So this is because the car's safety features are designed to transfer some of the energy into other forms, and this reduces the amount of energy transferred to the car passengers and to other road users to protect them. Now, resistive forces are forces that act on a moving body in the opposite direction to the direction of movement. Now, the main resistive force we know in situations is friction, which includes drag or air resistance. Now, when an object such as a roller coaster moves vertically without a driving force, any difference between a change in the gravitational potential energy and the kinetic energy corresponds to a loss of energy to resistive forces, or work done against resistive forces. So you could write this out as the work done is equal to the potential energy change plus the kinetic energy change, where the kinetic energy change is a positive and the potential energy change is a negative. Now, potential energies tend to be defined as negative values, as we define outside a field to have an energy of 0. So what this means is that energy has to be given to an object if it has potential energy to leave a field, so therefore potential energy must be a negative. Now, if we consider that an energy transfer has no drag forces present, we can then use our principle of the conservation of energy, where the loss in potential energy is equal to the gain in kinetic energy. So we can say mg delta h equals a half mv squared. Now the mass on either side of these equations cancel through to give g delta h equals a half v squared. So we can rearrange this equation to calculate our change in height. So delta h can equal a half v squared over g. Alternatively, the velocity of the object can be calculated. So v is equal to the square root of 2g delta h. Now these values produced for delta h and v assume that there is no friction present when work is done. Now some examples where these equations could be used include a swinging pendulum, objects in freefall, in sport which involves falling, such as skiing and skydiving. So to summarise what we've looked at in today's lesson, the kinetic energy of an object is equal to a half mv squared, the gravitational potential energy of an object in the uniform gravitational field equals mg delta h, and we know about the exchange between gravitational potential energy and kinetic energy. So if we've been successful and learnt in this lesson, we should be able to calculate the gravitational potential energy store in a system, calculate the kinetic energy store in a system, and calculate the values associated with the transfer of energy in a system. Hello and welcome to this video for the Forces and Motion module for the OCR A-Level Physics specification in the Work, Energy and Power submodule, looking at the topic of power and efficiency. So if we've been successful and we've learned in this lesson, we should be able to define the concept of power and the unit of the watt, define and understand the importance of mechanical efficiency, and calculate values using the concepts of power and efficiency. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification. We're going to be looking at 3.3.3 power, including power, the unit of the watt, P equals W over T, P equals FV, the efficiency of a mechanical system, and efficiency is equal to useful output energy over total input energy times by 100. Now, in any energy transfer process, the more energy transferred, the greater the power of the transfer process. This is because that the energy transferred, or the work done per second, is the power. So power is the rate of energy transfer, or the rate of work done. Now we can work out power with the following equation. Power is equal to work done in joules divided by the time taken in seconds. Now the SI unit of power is the watt. Now we define 1 watt as 1 joule of energy transferred, or work being done, in 1 second. So we can write 1 watt is equal to 1 joule per second. Now as we know that 1 joule is equal to 1 kilogram meters squared per second squared, this therefore means that 1 watt is 1 kilogram meters squared seconds to the minus 3. Now there are situations where a constant force must be exerted on an object to maintain its constant speed. Now an example of this is a car travelling flat along a road at a constant speed. Now in this situation, the resultant force on the object will be 0. Now the rate of work done by the forward force provided by the engine therefore must equal the rate of work done against the frictional forces acting on the car. So we can say that the work done by the engine is transferred into the internal energy of the surroundings by resistive forces. Now as a constant force F moves the car a distance x in time t, we can say that the work done by the force W is equal to the force times by the displacement, or in this instance F times by x. Now we have just said that power is equal to work done over time. Now we know the work done is Fx, so therefore the power is Fx over time. Now we know that velocity is equal to x over t, the displacement over the time. So we can sub that into the equation to say that power is equal to the force times by the velocity of the object. Now you can use this particular equation in a variety of situations where a constant force is necessary to maintain a constant speed. Now examples include a swimmer travelling through water at a constant speed and a skydiver falling through the air at terminal velocity. So not only is power in watts equal to work done in joules over the time taken in seconds, but power in watts is also equal to the force exerted in newtons times by the velocity in meters per second. Now remember that the force exerted must be in the direction of the motion, so we may need the horizontal or vertical component of the force. Now when a powered object moves at a constant velocity at a constant height, the resistive forces are therefore equal and opposite to the motive forces. So like we said before, we can say that the work done by the engine is transferred into the internal energy of the surroundings. Now this equation of P equals Fv is used when an object is undergoing constant velocity. So therefore the force exerted calculated could either be the motor force or the resistive forces, as they are equal in magnitude to each other. Now when a powered object gains speed, therefore the output force exceeds the resistive forces acting on it. Now, this therefore means that the work done by its engine increases the kinetic energy of the object and enables it to overcome the resistive forces acting on it. So let's have a look at a few examples of this. So consider the following. We're using a crane, and the crane lifts a load of 1,500 kilograms, a height of 25 meters, at a steady rate in a time of 2 minutes. What is the power of the crane? Well, we know the work done is the energy transferred, which is mg delta h, because we're looking at potential energy. So therefore it's 1,500 times by 9.81 times by 25. So therefore it is 367,875 joules. We can then use this to work out the power of the crane by doing power is equal to work done over time. So this 367,875 over 120 minutes into seconds. So therefore it's 3,066 watts. The next example looks at the following. What is the resistive force on a cyclist who has a leg muscles of power 200 watts each and who reaches a top speed of 10 meters per second on a level road while cycling? So we know that P equals Fv. So in this case, we can work out that F is equal to the power over the velocity. So it's 200 times by 2, as the cyclist has 2 legs, as shown in the image, divided by 10, so therefore our force is 40 newtons. Now the principle of conservation of energy states that energy cannot be created or destroyed, but energy can be transferred from one form to another form, but the total amount of energy in a closed system will not change. However, this doesn't mean that processes and machines convert all their energy into useful work. In particular, thermal losses can mean that some of the input energy is not converted into useful output energy. No device, with the possible exception of a heater, transfers all inputted energy into useful energy. Now, when it is stated that energy is lost, it means that the energy has been transferred into a form that cannot be used or transferred into a form that can easily be used. Now, often work done against friction will cause thermal energy to be produced in the energy transferred. Now, a measure of how much input energy is transferred usefully by a mechanical system is called efficiency. The more useful energy gained out of a machine for what you put in, the more efficient the machine is. So the greater the efficiency, the greater the percentage of input energy converted. So we can say that efficiency is equal to the useful output energy over the total input energy times by 100, or conversely, efficiency is equal to the useful output power over the total input power times by 100. Please note there are no units for efficiency, and efficiency can be expressed in terms of a decimal or a percentage. Now, due to the conservation of energy, efficiency can never be higher than 100% or 1.0. Now, the efficiency of machines or processes can be improved in most cases by insulating an object from heat loss. So let's look at an example calculation. Consider the following. A meat grinder has a useful energy output of 725 joules when making mincemeat. If its efficiency is 89.1%, work out the total input energy. So we know that if efficiency is equal to the useful output energy divided by the total input energy, well, therefore the input energy is equal to the useful output energy over efficiency. So it's 725 over 0.891. We've converted our percentage into a decimal. So therefore it equals 814 joules. So to summarize what we've learned in today's lesson, we've looked at the concept of power, the unit of the watt. Power is equal to work done over time taken. Power is equal to force times by constant velocity. The efficiency of a mechanical system, and efficiency is equal to the useful output energy over the total input energy times by 100. So if we've been successful and we've learnt in today's lesson, you should be able to define the concept of power and the unit of the watt. define and understand the importance of mechanical efficiency, and calculate values using the concepts of power and efficiency. So thank you very much for watching this lesson on power and efficiency, which is part of the work, energy and power topic in Module 3, Forces of Motion. Thank you very much and have a lovely day.